All right. So while we are waiting for the other people to come in, we'll officially start it at 5 minutes past the time. I want to take a little bit of a survey for the class. So we have about like 20-something people. So how many of you are interested in taking the class just because that'll get you a degree? Okay, 1, 2, 3, 4. All right. Okay, so good. So you're clever because for the rest of the people, I'm going to ask you why you're taking the class. What made you interested in taking this class? So I'll pick randomly, starting from you, please. You're one of the 4. Okay, how about you? Sorry, what's your name?
Gary.
Huh? Gary. Okay, cool. What's your name?
Danghua.
Danghua?
Yeah.
Danghua. Okay, so what made you interested in taking aerodynamics?
I just like things that fly. So I was like,
Oh, you like things that fly? Good. We will see a lot of things that fly in 1600. Okay, so how many of you are interested in taking the class just because you're interested in seeing things that fly? Okay. Okay, good. For the rest of the class, what made you interested in taking 6100? Yes?
I really like Formula 1. There's a lot of aerodynamics that come to cars. So it's a really interesting class.
Nice. You like things that drive fast, right? You like things that go fast. So that's good. We also see a lot of things that go fast in the lecture. Anybody else? Any other motivations for taking 16100? Yes?
I need it for my major.
You need it for your major? Alright, so that belongs to you. Yes, right now we still have 3 answers, right? 1 is I need it for my degree or major, right? The 2 is you like things that fly, and 3 is you like things that go fast. Anybody else? Yes?
Fluids was cool.
What? What?
Fluids.
Fluids.
The class was cool.
Okay, the class is cool. Fluids. I also, yeah, that's a good motivation. I also like fluids, and it's interesting that fluids involves in things that doesn't have to fly and doesn't have to go fast, right? So everything aerodynamics is actually related to fluids. So very good, very good. I think these are all very good motivations for why taking aerodynamics 16100. So we'll have classes on Monday, Wednesdays from now to it's a 90-minute class, but hopefully we'll break it down, have a lot of interactions, and I'll lecture for some time, and I'll ask you to form into groups of 2 or 3 and solve problems on the walls sometimes, so that 90 minutes hopefully is not as boring as I just lecture for whole 90 minutes. So my office is actually right across the hall, 33412A. So you can find me there. And hopefully, I think I'll hold office hours this semester downstairs in the Siemens lab instead of in my office, because usually looks like more people come to office hours if I hold it downstairs, right? So. And the office hour is still TBA, but my personal preference would be Monday right after class. How many people cannot come to office hours if I hold it on Monday right after class? Okay, that's actually, well, okay, that's actually quite a few. How about Wednesdays? Wednesdays I can actually not do it right after class, but I'll do it a little bit later after class, like 1 or 1:30. Would that work for more people or less people? So who cannot come, let's say, 1:30 on Wednesdays? How about 1? Looks it's very similar number of people. So Would you mind that maybe we can do a bit of survey, right? And you can also fix your office hour. By the way, this is our TA, Mohammed Islam. Would you mind to introduce yourself a little bit?
Yeah, sure. Hi everyone. I'm Mohammed. I'm a grad student in the aerospace department. I TA'd the course with Professor Wong last semester or last year. Yeah, happy to work with you. I'll be teaching the recitations and holding my own office hours as well. Nice to meet you.
Thanks. Yeah. So we'll post a survey, and since we cannot do it qualitatively, it looks like similar number of people cannot make it. So we'll make it more quantitative. All right. Okay. So we have two main web resources. One is on Canvas, and the one is Piazza. So, like I tried the various ways of doing basically substituting office hours virtually, and Piazza seems to be the one that works the best, right? We tried the Slack, we tried Piazza, we tried the discussion on Canvas, and somehow I think Piazza seems to be working the best, right? So have you all used the Piazza before? Yes, okay. So one thing I want to ask you is that the Piazza has this functionality of asking questions anonymously, right? So what I don't want to see is you ask me questions in like private questions, because I think whatever question you ask, even if you think it's stupid, it is often not stupid, and it will benefit everybody else. So if you don't feel comfortable asking with your name on it, just ask anonymously, but don't ask me privately on Piazza. All right. Okay. So that's the kind of overall course. So in terms of what we are going to be doing in 16100, I'm experimenting with organizing the course a bit differently every time. I this semester we'll split it into actually 4 different parts. The first part will deal with fundamental concepts. So today we are going to be discussing, for example, the applications of aerodynamic forces, right? That's kind of on the applied. So everything on the left is more applied track, like applied aerodynamics. That will directly address, for example, things that flies, things that go fast, right? When I hear these two motivations, I feel like it is very in tune of what we are doing in the applied track. Things that flies goes into lift, right? You need lift to fly. Things that go fast has to do with drag. I mean, you have to have low drag for you to go fast. So this is great. So today we're going to be talking about lift and drag, and then we are going to relate drag with energy consumption, right? So that's kind of the overall fundamental concepts for applied aerodynamics. But in order for us to especially go into the more advanced part of applied aerodynamics, right? For example, lift-induced drag, the aerodynamic shape of lift, and stability, etc. We have to understand a lot about the theories of how fluid moves. So that's why in the fundamental concepts, we actually, in the beginning part of this class, we'll do a lot of theoretical aerodynamics that includes kinematics, right? We'll be talking about substantial derivatives, and the words that looks very advanced is called Eulerian derivatives and the Lagrangian derivatives. So we'll be talking about the distinctions between those and how they are related to forces and conservation laws, right? There are actually 2 complementary ways of looking at the dynamics of fluid motion. One is using Newtonian laws, right? Basically F equal to ma. And for that, you need the Lagrangian derivatives. The other way, which is equivalent, is looking at conservation laws. For that, you need Eulerian derivatives. And then we'll look at non-dimensionalization and the sensitivity analysis. That is actually permeate through the entire applied track, all the way to the end when you're designing an airplane. Right? When you're designing an airplane, it's all about sensitivity analysis. If I change this by 1%, does my drag increase by 2% or 0.5%? Right? If I tune that by 1%, would that decrease by how much? Right? I mean, these are all about sensitivity analysis. And then we'll be talking about order of magnitude analysis and flow regimes, because that will really allow us to go into the different parts of applied aerodynamics. So basically, through order of magnitude analysis, you're going to figure out for this application, I can neglect, for example, viscosity. I can neglect compressibility, right? And then I'll just look at a incompressible potential flow. Or in some other applications, I cannot neglect, for example, viscosity or compressibility. Then we'll have to go into viscous and compressible flows. So these are then the second and the third modules of this class. So for the more simpler applications, we'll look at the lift-induced drag, the aerodynamic shape of lift. So essentially, why wings or any aerodynamic surface look like what they look like, right? And how does that affect lift and aerodynamic stability, right? I mean, like one way to look at an airplane is that you have a wing that's split into two parts, either a main wing and a canard, or a main wing and a horizontal stabilizer, right? Why do you do that, right? I mean, that's actually has to do with lift and how the lift changes when you increase or decrease the angle of attack. So these are in the incompressible potential flow section. After you learn this section, hopefully you would be able to starting looking at designing airfoils, right? At least for lift and for stability. And of course, in order for you to understand that, we also need the potential flow actually this is vortex dynamics, right? These are the theoretical part of incompressible potential flow. Any questions so far? Also, in terms of a lecture style, I want you to ask questions. Just interrupt me anytime to ask questions. You don't have to wait for me to ask you, right? Actually, usually I record my lectures and post them online. And if you don't ask questions, you can just not come to class and watch it online. And I mean, I have absolutely no problem with that, right? So if you do come to class, it's an excellent opportunity to interact and ask questions. All right, I mean, that's the only advantage of coming to class, right? Now we have all the video recording and the technology, right? I mean, just to think about why do you come to class. All right. Okay. Any questions? No? So the third module is viscous and compressible flows, right? So we'll look at high lift airfoils. So why can we not achieve arbitrarily high lift coefficients? Right? So what is limiting an airplane or any aerodynamic surface to, right, achieve a high lift coefficient, right? Why does the Titanic hit the iceberg? Well, you may ask, what does it have to do with high lift? Anybody has a clue?
It could have flown over the iceberg if it had a higher lift coefficient.
I'm sorry, that's not the reason. Stall? Right, what stalls?
The flow.
The flow over the rudder, right? So Titanic hit the iceberg because it could not turn fast enough. It could not turn fast enough because you don't have enough lift on the rudder, I'm going to talk about lift right in a few seconds, and I'll explain like why this has to do with aerodynamic forces and why it has to do with lift. All right, and then we'll talk about. So this is all about viscosity and flow separation, and then we're going to be talk about transonic and supersonic flight. So that has to do with compressibility, right? Shock waves and how they form, how they affect the drag and affect the lift. I mean, actually it has to do also with viscosity, because if you have a shock, it induces separation. It also limits how much lift you can get. Finally, I mean, this we might not have time to get to that. If we have time, we'll talk about unsteady flow and aeroacoustics, right? So, any sound you hear, the way I'm talking through sound, it's actually governed by fluid dynamics, aerodynamics, and it's unsteady fluid dynamics. So if we have time, we'll talk about how sound propagates and more interestingly, how sound is generated, right, through aerodynamic means. So after these 3 modules, we have the final module. That's a team design project. So I'm still working on finalizing what the design project is like, but most likely it'll be basically taking an existing airplane which is operated on fossil fuel and make it battery operated, right? So you look at the existing designs and see, use everything we've learned to figure out, okay, if I want to substitute the fossil fuel with batteries, okay, assuming all the propulsion units are, well, of course it's a big assumption, assuming the propulsion units still weigh the same and have the same power and thrust, okay, what do I need to modify? Do I need to make the wings bigger, smaller, right? Should it cruise at higher altitude, lower altitude, etc. All right, so that's going to be a team design project. Depending on how many people end up taking the class, we may have teams that are bigger size, smaller size. We'll see. All right. Okay, so that's the overall structure of the class from now to the end of the semester. There will be no final exams, but there is this team project, and there will be 2 quizzes. One quiz probably over here, and then a second quiz probably over here. The final score is going to be a composition of homework, quizzes, and your design project. All right. Now, any questions? Yes.
What's the weighting between the homework quiz and the project?
I forgot. I'm going to be using the same weighting as we used before. So I'm going to post the syllable later tonight, and you're going to see it from there. All right. Any other questions? Yeah, Mohammed, meanwhile, can you just look up the syllable? I mean, right now it's a draft, right? But I think the weighting is already there. Yeah, if you can look it up, you can tell everybody. All right, if no questions, we'll go to the first part. So that's the application of aerodynamic forces. It's going to be the fundamental concepts. Okay, what aerodynamic forces are there? To start, we are just going to be talking about lift and drag. All right. And what you're going to see is that if you understand the lift and drag, you're going to have a very good understanding of all other types of forces that are aero in origin, right? Forces that are, for example, thrust, right? You may think of it as an aerodynamic force, but if you look in detail, it's basically a very complex composition of lift and drag. So here we are just going to tell you, that's too colorful, what is lift and what is drag. Since all of you are supposed to have taken unified, can somebody tell me what is lift and what is drag? So first of all, lift. What is lift? Yes.
The thing that makes the plane go up.
The thing that makes the plane go up. That's correct in the context of airplanes. Well, but there is actually a more, so in 6100, right, we are going to be using a more general definition. So somebody, I remember somebody interested in race cars, right? Who was that? What's your name? Alonso, okay. So Alonso, do you know race cars generate any lift?
They generate what they call downforce. It's like you flip essentially an airplane upside down and it gets forced downwards.
Exactly. So for everybody who doesn't know, a race car also has wings, but flipped upside down. So it also generates what we call, in terms of aerodynamics, what we also call lift. But the lift, instead of pointing upwards, it points downward, right? So what's common between the lift that lifts an airplane and the lift that pushes down a car? Yeah?
It's perpendicular to the direction of motion.
It's perpendicular to the direction of motion. Exactly. So that's actually the definition of aerodynamic lift. So take note, because I'm going to be asking you a lot of questions that you are going to use this definition. Okay. So force, so aero force, aerodynamic force. Perpendicular, so I just use this sign, to what? To the relative direction of motion. Okay, so every word here is important. So first of all, what is aerodynamic force? Well,
From air.
it's from air, right? It's a force exerted by air to some solid object. But that's the aero part. What is the dynamic part? You have to be moving, right? So for example, buoyancy is also an aero force, right? The force that lifts a balloon is also aero force, but it is not aerodynamic force because it is still there when you're not moving. So aerodynamic force is a force that exists on the solid body only when the solid body moves relative to air. Right, so that means there is a relative motion between the solid object and air. Okay, then the relative direction of motion. That's actually the relative is important. It doesn't have to be perpendicular to the absolute direction of motion, right? Because if you understand the fundamental principle of how Einstein derived the relativity, like all the physics are the same if you choose a different frame of reference. So the only important thing in terms of aerodynamics is what is the relative motion between the solid object and the air, right? So it's aerodynamic force perpendicular to the relative direction of motion. Now, once we understand the lift, drag is easy. It's just the aerodynamic force in the only other direction. What is it? It is the aerodynamic force along, right, parallel to the relative direction of motion. So aerodynamic force parallel to the still relative direction of motion. Any questions before we go to I test whether you understand this or not? Yes?
So would that technically mean that if you were, let's say, just going forward and a force to the left or to the right, since that's also perpendicular, would be considered like?
Yes. So if you are moving forward, right, and assuming there is no lateral wind, all right, because if there is a lateral wind, then the relative direction of motion is no longer forward, right? So assuming you have no wind, you're going forward, the force that pushes left or right is actually lift. Exactly. Okay, that's actually a very good question that basically already partly answers one of the questions I'm going to ask you later. All right, good. Any other questions? Yes?
So can it just be described as parallel perpendicular to the free stream then? Or is that like not?
That's correct if your solid object is not moving.
Okay.
All right, if your solid object is not moving, or you choose a frame of reference that moves along with the solid object, then yes, the force that is perpendicular or parallel to the direction of the air is actually lift and drag. Yeah, good point. Yeah, or on the other hand, if the air is not moving, only the solid object is moving, then the aerodynamic force is perpendicular or parallel to the direction of the solid object movement, is lift and drag. Okay, any other questions? How many of you came to here because you're interested in space applications? Oh, pretty much. Okay, so I'm going to ask you about the aero forces involved in here. What are the lift and what is drag, right? Somehow I don't have. Does that work? Oh, that works. You see this grid thing moving, right? Guess why are they moving? In terms of, can you explain why the grid things are rotating based on aerodynamic forces? Anybody want to volunteer? What forces is it trying to generate by rotating these grid things? Yes? Drag? All right, the grid thing is actually generating drag, no question, because of course let me see. So the rocket is moving down, right, towards the landing pad, right? The grid thing is actually faced right against the relative motion of this grid thing to the air. So you can actually see these cloud kind of going through the grid thing, right? That actually is a very good visualization of what is the direction of motion, what is the relative direction of motion. So what direction is the drag forces? It's like along this way, right? But that doesn't explain why the grid thing rotates, right? I mean, it generates drag pretty well without rotating. Yes? It produces lift, right? In which direction is the lift? Yeah?
I guess we were talking about this left and right, just to rotate the rocket, I guess.
Yes. So if you, I don't know if you can see carefully through here or not. Let me see. If you look at the flow direction as it rotates, see, do you see this flow direction being, do you see the flow being turned as the grid thing is rotating? Right? So if the flow is turned by the grid thing rotating, the grid thing is actually impacting a momentum change to the flow, right? Okay, and according to Newton's law, the flow is then impacting an equal and opposite force to the grid thing. Not just in the direction of the relative motion, but also perpendicular to the direction of relative motion, right? That's actually lift. So the rocket, the grid thing, is using lift to actually direct the orientation of the rocket, right? Because the rocket is very long. If for example, if you rotate both grid things that way, right? You get force operating on the top side of the rocket that way. So that will rotate the rocket. It'll rotate the thrust of the rocket that way, right? So I mean, this is essentially using lift to control the orientation of the rocket. All right, so that's a space application. Of course, we are all very familiar with the aero forces that flies an airplane, right? So the lift, of course, points upward or mostly upward, right? Why do I say mostly upward?
Exactly parallel to the ground.
Yes, it depends on the flight path, right? If the airplane is climbing, then the lift forces would point not exactly upward, but slightly in which direction? Slightly backward, exactly. If the airplane is descending, then the lift would point slightly forward, right? That's why you need more thrust when you are climbing, and you can basically glide, right, when you are descending. Because, right, when you are climbing, the lift force is pointing backwards, and you need thrust to overcome that. When you're descending, the lift force points slightly forward, and that overcomes, right, partly. Well, I mean, if you do a force decomposition, I mean, it doesn't overcome the drag, but like the force that points forward, the drag points slightly backward, the gravity points straight down, right? Everything balances out. That's how you glide. All right. One thing that that's very unique about the lift force is that because it is perpendicular to the direction of apparent motion, it is very efficient in the sense it doesn't, if an airplane has no drag and only lift, it can stay afloat without consuming any energy. All right. So just to think, contrast that with an alternative of an airplane that has no wings but has a jet engine that rotates and points downwards to generate all the lift or all the lift it wants, right, for sustaining a level flight. That requires a lot of energy, right? While if you sustain the flight of an airplane through pure lift, it actually requires no energy, right? So we'll also think about that when we answer later questions. All right. Now let me ask you to watch another video and ask you what lift forces are doing over there. Anybody seen this? Okay. So, quite amazed that it's actually still in theater, this. Okay, something seems wrong, and let me see if I can.
Driver to range control. Entering point alpha. Confirmed green range.
Range control. Green range is confirmed. I don't see an event schedule for you, sir.
I'm sure lots of you have seen this before, just to focus on what the lift is doing, right? Think about the definition.
That's impossible. File attack point. Mavericks inbound.
Okay, what is the lift doing now? Yeah, let's. Okay, so let's stop here a little bit, right? So we've seen Tom Cruise flips upside down, right, and goes like that. Why does he flip upside down? Yes?
So it feels more natural to him rather than being directed like into the ceiling.
Okay, it feels more. That's actually part of the reason, but that's not an aerodynamic reason. I think you raise your hand next.
Yeah, if he flips upside down, the lift is pointing like towards the center of the circle that he's turning. It's kind of like a banked turn, so it's like helping him go force to turn faster.
Right. So that's an aerodynamic explanation. If you flip upside down, the airplane is more efficient in generating lift towards its upside, right, towards Tom Cruise's head. So that way, like, it provides the centrifugal force. I mean, centripetal force for him to turn in a tighter circle. Yeah, somebody else?
I was just going to say it prevents G-loading on the structure.
What?
It prevents excess loading on the structure.
Oh, that's also true, right? Because even if the airplane is capable of generating as much lift, if it goes like that, right, the structure is actually more designed towards having a high G load, right, in that direction. So that's also part of the reason. But I think you're Alonso?
Yes.
Yeah, Alonso provided the aerodynamic reason of why he flips upside down. Then what we see is that, okay, when he's in this simulated canyon, okay, he banks side to side. Right? Why does he bank side to side? I think you raised your hand first.
To direct his lift sideways.
To direct his lift sideways. Again, that provides the centripetal force for him to turn in a tight circle. All right. So that's actually many different ways an airplane uses its lift. Right, by actually just pointing the lift direction into different ways, it does the maneuver basically. So let's just keep thinking about this and watch the rest of this clip. Okay, so watch this. I'll have a question right in a few seconds, right? So I'll not ask the question now, but focus the next few seconds because that will involve a question I'll ask you later. When he pulls up.
Counting 3, 2, 1.
Again, like a turning over, right? All right. Any questions so far on this? What?
So can we watch the whole movie?
You need to buy a ticket. It's still in theater. Just to go tonight. Wait, what happened?
Your browser is still open.
Oh, okay. I don't know. All right. Okay, so the question I want to ask you, like when I when I prompt you is over here. So just rewatch the next few seconds of this. All right, so see what's happening to the air over here? Okay, so what I want to ask you is from this scene, I want you to do an analysis to figure out how big the lift force actually is. All right, so I want you to think about the following two questions. One is, can you estimate what is the mass of air? Right, so it's obvious, like there is this mass of air as Tom Cruise pulls his stick. This mass of air. So we'll talk about how like the airplane moves, sets the mass of air in motion later on. I mean that's kind of in the second module, right? But now it's obvious he sets in motion a mass of air, right? So the question I want to ask you is, how big, what is the mass of air set in motion by his airplane, let's say in 1 second during this pull-up? Now assuming, okay, the air set in motion moves downward, right? Because I mean, to generate lift, the air is probably moved downward, right? So let's say the downward velocity is 1% of the speed of his airplane. Calculate the lift. All right. So what I'll ask you to do is I'll ask you to form groups of 3 people and come over to the edge of the classroom. I'll go grab like pieces of paper to put on the board, and you're going to be I'll also grab you some markers, so you're going to be working groups of 3 to figure out this calculation.
How much air? 1 second. Yeah, 1 second.
Well, look at what I'm doing.
Okay, how fast? By 1 second, you have to answer 1 second. What? By in 1 second. Oh, I almost died. That's the
Tom, who has answers to both questions? I mean, any answer is fine, right? It doesn't have to be. You don't have to have 100% trust in your answer.
Like you can tell me it's right or it's
All right. Okay, I think maybe I think over 50% are done. So let's actually get back because we are going to have the end of the lecture in like 10 minutes. Let's collect from team to team what the answer is. So I don't want a numerical answer. I just want a formula, right? I just want a formula in terms of V, B, and the rho. So can I go from over here? So in this group, who works on this group? Yeah, can you tell me what is your formula of how much lift you get? I mean, Tom Cruise gets.
We have 0.005 v squared rho.
B squared V squared rho. Okay, thanks. Who works on that one? The one closest to me on the board. Yeah. What answer do you get?
We did it in we got a numerical answer. It's 25,000.
Okay. Do you remember is there a formula?
No, we were actually estimating. We didn't see the last part about the variables.
Okay, I give you 5 seconds to derive the derive the formula. Anyway, 5 minutes. So who works on the middle one? Yeah, can you tell me your answer? times the reference area. So I would just say B squared has the reference area. How about that? That's the mass of air disturbed per second. Okay, good. Who works on that one, like over there near the window?
Yeah, that was us. It's pretty much the same, but we did 3/2 B times rho times B squared.
3/2 B squared times rho times
V.
V?
Yeah.
There is no squared on the V?
Which question are we answering?
The second one.
I'll answer the second one.
Oh, the second. Okay. Yeah. So the second is okay. B squared. And do you get the answer to the first question? To the second question? Sorry. Huh? How about the second one? How about the? Why don't I get an eraser?
So for lift, that 3/200 times B squared times B times rho times G times 1 second.
Times G times 1 second. Okay. All right. So let me just say this is. No, that's not what I want to delete. So this is lift. This is mass per second. All right. What else? How about that? That part.
Yeah, for the mass we had same B times rho times B squared, and then
So sorry. Can you say again?
just the same as the first one. It's B times rho times B squared,
Okay. How about lift?
and then we were just kind of going for order of magnitude. So you said 0.01 B squared times rho.
All right. You have a question over here? Did I get
I'm
it?
just asking where we got the B squared.
Okay. Okay. So are you asking me to explain why we get a V squared?
He was asking.
Yeah, I was just asking why he got, because I got a really close answer for it.
Okay.
I was just saying that like we multiplied them because it's the mass. The initial answer is mass per second. Right?
Mhm.
I mean, it's only the mass because it's over 1 second.
Mhm.
And then m dot v. So normally that'd be m dot, and you just multiply by v to get like the imparted momentum, or I guess force.
Yeah. Good. I'll talk more about that later. We have, I think, several more over here. How about that one? Who works on that one? Can you shout the answer? If you have the answer for the lift, just shout out the lift.
Yeah. It's the same as the one right above. 0.01 B squared B squared.
Okay. Thank you. How about on the blackboard written in chalk? Do I can actually almost see it.
For the lift, we got 0.025 B squared B squared.
Okay, good. How about the one? Do we have an answer for the paper here? Yeah.
We got 0.01
V squared rho. Okay. How about this one? The one?
Same thing.
Same thing. Okay.
Yeah.
How about
That's
the?
also us, yeah.
That was also yours. Okay. How about here? Oh, here we.
That's the same thing.
Oh, also exactly the same thing. Okay, so good. We have almost a consensus on how much lift there is, right? And there is a question actually on why there is a squared on the velocity. So I would say this one is an exception, and if you can figure out what you did wrong, that'll be good. But for all the others, we get the B squared, which is a area unit, right? And the V squared and the rho. So let's think about why we get an answer like that. So first of all, rho is obvious, right? I mean, if you deflect the same amount of air, the denser the air is, the more momentum you get. Therefore, the higher lift you get. Okay, and B squared is also kind of obvious, although there is actually a lot of math and geometry in that. So the cross-sectional area of the column of air disturbed is proportional to square of the span, right? We'll wait till we get into vortex dynamics to figure out why that is the case. right? But like it's also kind of intuitive, right? You're disturbing almost like a column of air. I mean, it's actually not exactly a column of air because in fluid mechanics, nothing is actually like a solid body, right? You have high velocity in a column of air that's almost like a cylinder with diameter equals to b. But the more towards the edge, the smaller the velocity is, and even outside the column, you get a smaller and smaller velocity all the way to infinity, right? So in fluid dynamics, you have a lot of vector fields like that. We'll have to wait until almost the midterm, right? The middle of the course to figure out why that is the case. But it's obvious why b squared, right? But why v squared? I think you already provided an explanation. Can somebody else? Yes?
Well, the momentum of the air you're moving is, changes with v, as does the amount of air you actually move.
Yes. So it comes, the v squared actually comes from two separate sources. It's v times v. The first v, I mean, you can flip it over. The first v comes from the volume of air. Is proportional to v, right? The faster you go, the more air you're disturbing per second because you're actually passing through more air. The second v comes from how much you are disturbing the air. The faster you move, the faster the air actually gets pushed down. That's why there is a v squared. Okay, so the end result is aerodynamic forces. So both lift and drag is proportional to rho v squared times area, right? Rho v squared times area. And to be more precise, it is equal to, I mean, if I change this to equal to sign, you are multiplying this by half of lift coefficient, half of drag coefficient, no, not d, but the CD, drag coefficient. All right, so this is actually where the lift coefficient, drag coefficient come from, right? I mean, through a dimensionality analysis, I mean, here we did with lift. You can do it with drag also. We're actually going to do it probably in a later lecture. You're naturally going to get this unit, right? How much aerodynamic forces you get is always going to be proportional to the density times a squared velocity times a certain area, no matter if it's the square of the wingspan or some other area you get. So this is how much aero forces are there. Okay, to end this lecture, I'm going to skip this. I'm going to basically trying to let you watch a video. I don't know if you've seen something like that before, but it's actually a view of a helicopter blade. With a camera actually mounted on the blade. So here, what you're seeing is the helicopter blade is generating lift, right? I mean, just imagine the relative motion between this blade. Now we are taking a reference actually that moves with the blade and air, right? As the helicopter is flying forward, and there is one velocity of the whole helicopter, there is another velocity of the blade. And then you are composing the velocity, that's kind of the relative velocity of the air with the blade. And then the lift is the aero force, the aerodynamic force, orthogonal to that relative motion. And for that helicopter, most of it is pointing upwards. All right, so here's kind of, basically we went through a lot of applications of aero forces, and especially kind of did the dimensionality analysis of how big the forces are, right? And starting from next lecture, we are going to actually dive into some of the fundamental mathematics of what is generating the forces, and come back to especially looking at drag and how that relates to energy consumption. So that'll be next week. And this Friday, Mohammed, I think something you also did last time is to host a recitation session that reviews the unified fluids, right? So we'll do the same thing this Friday. Okay. So if you're worried about this part, do come on Friday. All right.